In this lesson and in this series of lessons, we are going to talk about sorting algorithms. Sorting as a concept is deeply embedded in a lot of things that we do. It's quite often that we like to arrange things or data in certain order, sometimes to improve the readability of that data, at others to be able to search or extract some information quickly out of that data. For example, something as simple as when we are playing a card game, even though the number of cards in our hand is really less, we like to keep our hand of cards sorted by rank or suit. So let's say this is our hand of cards and we would like to keep it in increasing order of rank, then the arrangement will be something like this. Now have a look at this. When we go to a travel site to book a hotel, and then the site gives us all these options of sorting the hotels by price from low to high, or by star rating, or by guest rating. So right now I have my options sorted by guest rating, so the hotel with the highest guest rating is at the top. I may be on a budget and I may want to avail the cheapest option, so I would sort the hotels by price from low to high, and now the cheapest hotel will be at the top. And I may still try to strike a balance between rating and price. So sorting is a really helpful feature here. And there are so many places where we like to keep our data sorted. Be it a language dictionary where we want to keep the words sorted so that searching a word in the dictionary is easy, or something like a medal tally where we want to see which team is at the top and which team is not performing so well. If we want to define sorting formally, then sorting is arranging the elements in a list or collection in increasing or decreasing order of some property. The list should be homogeneous, that is, all the elements in the list should be of same type. To study sorting algorithms, most of the time we use a list of integers, and typically we sort the list of integers in increasing order of value. So if we have a list of integers like this, 2, 3, 9, 4, 6, then sorting it in increasing order of value will mean rearranging the elements like this. Sorting the list in decreasing order of value will mean something like this. And as we have said in the definition, we can sort on any property. What if we want to sort this list on the basis of, let's say, increasing number of factors? So the number with lesser number of factors is towards the beginning of the list. If you see, 2 has got only 2 factors, 1 and 2 itself. 3 has also got only 2 factors, 1 and 3 itself. 9 has got 3 factors, 1, 3 and 9 itself. 4 again has got 3 factors, 1, 2 and 4 itself. 6 has got 4 factors, 1, 2, 3 and 6 itself. A sorted list is a permutation of the original list. When we sort a list, we just rearrange the elements. Now this was a list of integers. We may have a list of any data type. We may want to sort a list of strings or words in lexicographical order, the order in which they will occur in dictionary. A list of strings like this in lexicographical order will be arranged in this order. And we may have a list of complex data type as well. A hotel object in the hotel list that we had seen earlier was a complex type. Hotel will have many properties, like its price, its distance from the city center, its guest rating, its star rating, and the list can be sorted on any of these properties. Sorted data is good not just for presentation or manual retrieval of information. Even when we are using computational power of machines, sorted data is really helpful. If a list is stored in computer's memory as unsorted, then to search something in this list, we will have to run linear search. In linear search, we start at the first element in the list and keep scanning the whole list until we get the element that we are looking for. So in the worst case, when an element will not be there in the list, we will compare it with all the elements in the list. We will scan the whole list. So if there are n elements in the list, we will make n comparisons in the worst case. And think about the kind of data that modern day computers deal with. What if this n is really large? If we take n equal 2 to the power 64 and imagine that one comparison takes 1 millisecond, then we will take 2 to the power 64 milliseconds. If you try to convert this to seconds, hours, days, and so on, this will amount to some years. If our list, however, is sorted, we can use something called binary search, And with binary search, if size of the list is equal to n, it will take only log of n to the base 2 comparisons to perform a search. So if n is equal to 2 to the power 64, we will take only 64 milliseconds. I had taken n equal 2 to the power 64 earlier to be able to perform this log quickly. Sorting as a problem is well studied, and a great deal of research has gone into devising efficient algorithms for sorting. In this series of lessons, we are going to study, analyze, and compare these sorting algorithms. Some of the sorting algorithms that we will be talking about, that we will be analyzing, are bubble sort, selection sort, insertion sort, merge sort, quick sort, heap sort, counting sort, radix sort, and this is not all. There are more, and you can imagine how important sorting as a problem is. We have so many algorithms for sorting that have been designed over a period of time. We often classify sorting algorithms based on some parameters. The first parameter that we want to classify upon is time complexity, which is the measure of rate of growth of time taken by an algorithm with respect to input size. Some algorithms will be relatively faster than others. The second parameter that we use for classification is space complexity or memory usage. Some sorting algorithms are in place. They use constant amount of extra memory to rearrange the elements in the list, while some sorting algorithms like merge sort use extra memory to temporarily store data, and the memory usage grows with input size. The third parameter that we talk about is stability, and this one will take some explanation. Suppose we have a set of cards like this, and we want to sort these cards in increasing order of rank. We have 1 3 of diamond, we have 1 9 of spade, and we have 2 6s, one of club and another of heart. One possible permutation will be this. The cards are sorted by rank. We have got 3 6 6 9, but if you see in the original list, 6 of club was coming earlier than 6 of heart, but when we have this permutation, which is a sorted arrangement, 6 of heart, this particular card, has come before 6 of club. A stable sorting algorithm, in the case of equality of key or the property upon which we are sorting, preserves the relative order of elements. So if the key is equal, if an element was coming before in the original list, it will also come before in the sorted list. A stable sorting algorithm guarantees that. So if we will use stable sorting algorithm, we will get this particular permutation where 6 of club will be before 6 of heart. The next parameter of classification is whether a sort is internal sort or external sort. When all the records that need to be sorted are in main memory or RAM, then such sort is internal sort. And if the records are on auxiliary storage like disk and tapes, quite often because it's not possible to get all of them in the main memory in one go, then we call such a sort external sort. There is one more parameter upon which we may classify sorting algorithms, and it is whether the algorithm is recursive or non-recursive. Some sorting algorithms like quick sort and merge sort are recursive, while others like insertion sort and selection sort are non-recursive. We will study all these properties in detail as we will study these individual algorithms. This is it for a basic introduction. Thanks for watching. In our previous lesson, we tried to understand the importance of sorting as a computational problem. We have so many sorting algorithms designed over a period of time, mostly to improve upon the previously designed algorithms. Now we will study and analyze these algorithms one by one. And the first one that we want to talk about, that we will be covering in this lesson, is selection sort. Selection sort, in my opinion, is the simplest sorting algorithm, and this is what one would do most intuitively. Okay, so let's get started. Let's think of a simple sorting scenario. Let's say we have a set of cards and we want to arrange these cards in increasing order of rank. One simple thing that we can do is, initially we can keep all the cards in our left hand, and then first we can select the minimum card out of these cards and move it to the right hand. Now once again, from whatever card is left in the left hand, we can select the minimum and move it to the right hand. next to previous cards in the right hand, and we can go on repeating this process. So at any stage during the process, the left hand will be an unsorted set of cards and the right hand at any stage will be sorted set of cards. So after 3 and 4, 6 will go to the right hand and finally 9 will go. So in the end, right hand will be a sorted arrangement of cards. Cards will be sorted in increasing order of rank. Now let's say we want to write program to sort a list of integers given to us in the form of an array. Something like this. We have an array of 6 integers here. So we have indices from 0 to 5. Let's name this array A. To sort this list, we can do something similar to what we were doing for our cards example. We can create another array of same size as A. So we have another array of size 6. Let's name this array B. Now we can start creating B as a sorted list by selecting the minimum from A at each step. There will be multiple passes on A. In the first pass, 1 will be the minimum. So 1 will go at 0th position in B. Now there should be a way to mark that 1 has already been selected, so it is not considered the second time. One way to do this can be, we can replace the selected element by some very large integer that is guaranteed to be the maximum in the array at any step. We can choose this max to be something like the largest possible value in a 32-bit integer. And now we will scan A again for the second largest element that will go to the 1th index in B. That element will be 2. So 2 again will be replaced by max, and now the minimum is 3, and we will go on doing this until all the positions in B are filled. In the end, we can copy the content of B back to A, so A itself will become a sorted arrangement of its initial elements. This logic will work fine, but if you see, there is this extra memory requirement for this auxiliary array or this temporary array B that we are creating, and larger the size of A, larger is the extra memory requirement for creation of this temporary array B. So this is not an in-place sorting algorithm. An in-place sorting algorithm takes constant amount of extra memory for sorting a collection. In this case, the amount of extra memory will be proportional to the size of the input array A. We can do something similar where we will select the minimum element at each step, but we will not have to use this extra array, this extra memory, and the algorithm will be in place. I have drawn this unsorted list again. What we will do now is, once again we will look for the minimum element in the array. So we will scan the whole array to find the minimum. The minimum in the array is 1. Now instead of filling up 1 at 0th position in another array B, what we can do is we can swap 1 with the element at 0th index, because that's where 1 belongs. It belongs to 0th index. So 1 goes to the 0th index and 2 comes to index 3. Now we need to look for the next minimum, and 1 need not be considered. And if you see, it's pretty easy now. We can scan all the elements from 1 to 5 in order to find the second minimum. The minimum in the range 1 to 5 is 2 at index 3. Now 2 deserves to be at position 1. So what we can do is we can swap 2 with the element at position 1, which is 7. This is how things will look after swapping. So second minimum goes at second position, which is index 1. And now we have to look for the next minimum in index range 2 to 5. So as you can see, in each pass we are finding out the element that should go to a particular position, and at any point during this whole process the array is divided into two parts. Some part of it is sorted, so the cells in brown here are sorted. With each pass we add one more cell to the sorted part, and eventually the whole array will be sorted. The minimum in the range index 2 to 5 is 3, so 3 needs to go at position 2, so it needs to be swapped with 4. Now we are sorted till position 2, and we will go on like this. 5 is at its appropriate position, it does not need to be swapped. If we have n elements, after n minus 1 passes we will have only one more cell left, so that anyway will be at its appropriate position. So finally our list is sorted. This particular in-place logic of selecting the minimum in each pass and putting it at its appropriate position is selection sort algorithm. Let's now quickly write pseudocode for this algorithm. We will write a function named selection sort that will take the array and the number of elements in the array as argument, and the logic will go something like this. We will run one loop with a variable I starting 0 all the way till n-1, and in each iteration of this loop we will set the element at ith position appropriately. And so first we will put the minimum at 0th position, then we will put the second minimum at 1th position, and so on. In fact, we only need to run this loop till n-2, because once we are done with all i's till n-2, n-1, the element at position n-1 will anyway be appropriate at the correct position. Now inside this for loop we will have another variable that will store the index of the minimum element. For ith element, to find the minimum, we will scan the array from I till n-1. So what we can do is, initially we can say that ith element is the minimum element, and then we can run a loop from I plus 1 till n-1, and while scanning, if we find any j that is having an element which is lesser than the current minimum, we will update this particular variable imin, and when we will come out of this second for loop, imin will have the index of the minimum element. Now we will have to swap it with element at ith index. We will do so using a temporary variable, and this is how our function will look like. I'll quickly run this logic in a real C++ program. I have written this function selection sort. In the main method I have created an array of 6 elements. This is the same array that we had picked up as example, and then I'm calling the selection sort function, passing the array and the number of elements, and once I sort the array, once I have sorted the array, I'm printing the elements. When I run my program, this is the output. So this seems to be working. The time complexity of this algorithm will be big O of n square. We can quickly see how. The running time is the total running time of all the statements. Let's say this particular statement will take some constant time c1 to execute. Let's say these statements will take at max c2 to execute. I'm assuming their running time together in the worst case, and let's say these statements will take c3 time in the worst case. This particular statement will be executed exactly n-1 times. This will also be executed n-1 times. This set of statements, this set of 3 lines, if we try to calculate how many times these 2 lines will be executed, it will be n-1 for I equals 0, n-2 for I equal 1, n-3 plus I equal 2, and this will be an arithmetic progression. We will go till 1 for I equal n-2, and this will only be equal to n into n-1 upon 2. So overall time taken will be something like this, and if we will evaluate this, this will be some polynomial like an square plus bn plus c, where a, b and c will be some constants in terms of c1, c2 and c3. And whenever we have a time expression like this, it belongs to the set big O of the highest order term in the polynomial. So this particular polynomial belongs to the set big O of n square. If you do not know about big O notation and time complexity analysis, we have one complete series on time complexity analysis. You can find a link to it in the description of this video. Selection sort is a slow sorting algorithm. Big O of n square is not the best running time for a sorting algorithm. So this was selection sort algorithm and its time complexity analysis. We will discuss more sorting algorithms in the coming lessons. Thanks for watching. In our previous lesson in this series on sorting algorithms, we had discussed selection sort algorithm. Now in this lesson we are going to discuss another sorting algorithm named bubble sort. So once again, let's say we have a list of integers given to us in the form of an array, something like this. Let's name this array A. We have 6 elements in the array, so we have indices from 0 to 5. Now we want to sort this array, so we want to rearrange the elements in the array in increasing order. What we are going to do in this algorithm is we are going to scan the array from left to right multiple times. We will call each scan one pass on the array. It's like we will first look at the 0th element and then look at the 1th element and then the element at index 2 and so on. Of course, we will not scan the array for no reason. What we will do is, when we are scanning the array and when we are at a particular position, we will compare the element at that particular position with the adjacent element at the next position. So if we are at 0th position, we will compare the element at 0th position with the element at 1th position. And if the element at the current position is greater than the element at the next position, we will swap the two elements. In this case, 2 is not greater than 7, so we will not swap the two elements. We will just move on to the next position, which will be position 1. Once again, we will compare the element at this position with its next element, and if it is greater, we will swap the two elements. In this case, 7 is greater than 4, so we will swap the position of these two elements. So 7 will move to index 2 and 4 will move to index 1. And now we will move to index 2. The number at index 2 at this stage will be 7. Once again, we will look at the next element. It's 1. 7 is again greater than 1, so we will swap. And now we will move to index 3. Once again, at this stage, the number at index 3 is 7. We will compare it with 5 and we need to swap again. So 7 will go to index 4 and 5 will move to index 3. And now we will go to index 4. As you can see, this whole process is pushing number 7, which is the largest in the array, towards higher indices at each step. When we are at position 4, once again 7 is greater than 3, so we will swap. There is no next element for index 5, and at this stage we are done with one pass on the array. And what has happened after this one pass is that 7, which is the largest in the array, is at its appropriate position. It deserves to be at position at index 5 in the sorted array, and that's where it is. So 7 has kind of bubbled up to the rightmost position in the array with this whole logic of swapping the adjacent elements. This was our initial array, and after first pass we have gone to a state like this. If I quickly have to write pseudocode for a pass, it will be running a loop something like this. We will run a loop from 0 to n-1. Let's say n is the number of elements in an array, and if ei, the element at position I, is greater than element at position I plus 1, we will swap the two elements. There is one minor bug here. If I is equal to n-1, it will be the last index, so there will be no element after that. So we will not be able to access ai plus 1. So we will run this loop only till n-2. We don't want to access an index that will be out of the bound of the array, out of the range of the array. For I equal n-1, ai plus 1 would have been out of range. Okay, so this is the state of the array after one pass. What if we perform another pass and once again keep comparing the adjacent elements and performing swaps? If we will do so, now the second largest element in this example will end up at index 4. The second largest in the array is number 5. So after second pass, our array will be in a state like this. With every pass on the array will be divided into two parts. One part will be the sorted part and another part will be unsorted part. After two passes, the part of the array from index 4 till 5 is sorted and the part of the array from index 0 till 3 is unsorted. With each pass, the largest element in the unsorted half will bubble up to the highest index in the unsorted half. So in third pass, number 4 should bubble up to position 3, index 3. And while scanning, once we reach to the part where we are already sorted, there will be no swapping. We can actually avoid going to the sorted part. It will only improve our algorithm. To pass 3, our array will be looking like this. In fact, we are already sorted. In general, if we will conduct n-1 such passes for an array of size n, we can say something like for k 1 to n-1, or we could say for k 0 to n-2. After n-1 passes, we are guaranteed to be sorted. So this is our pseudocode for bubble sort algorithm. Given an array and the number of elements in the array, this function bubble sort will sort the elements in the array in increasing order. Let's now try to analyze the time complexity of this algorithm. The running time of this algorithm will be the running time of these statements inside the nested loop. Let's assume that these statements will take constant time c in the worst case. These statements will execute in constant time. Now the first loop will run exactly n-1 times, and the second loop will also run exactly n-1 times. So the total time taken as a function of n will be n-1 into n-1 into c, which will evaluate to cn square minus 2cn plus 1. Whenever we have a polynomial expression for time, then we say that the time complexity is big O of the highest order term in the polynomial. The highest order term here is n square. We just remove the constants and we say that this running time will fall into the class big O of highest order term. In this case it will be n square. If you do not know about big O notation or how to calculate running time of algorithms, we have a whole series on time complexity analysis. You can find a link to it in the description of this video. Big O of n square is not the best running time for a sorting algorithm. In fact, this running time is bad. Bubble sort is a slow sorting algorithm. It's as good as selection sort, but both bubble sort and selection sort are slow sorting algorithms. We can do a couple of things in this algorithm to improve the time complexity, at least for some scenarios. The first thing that we can do is we need not run this second loop all the way till n-2 all the time. As we had discussed earlier, at any stage during the sorting, the array will have some part as sorted and some part as unsorted. There is no point passing through the sorted part because there will be no swapping in that part. For first pass, we can run this inner loop till n-2. For the second pass, we can run this inner loop only till n-3 and we will be good. For the third pass, we can only run till n-4 and so on. So in general, we can run this loop till n-k-1. So when k is 1, we will run till n-2. When k is 2, we will run till n-3 and so on. This is some improvement. But in this case also, if you would calculate the time expression, it will be some polynomial of the form an square plus bn plus c. So complexity will still be big O of n square. We can do something else to improve this algorithm further. If you remember the example that we had picked up, it was sorted after 3 passes only, and 4th and 5th pass was only redundant. If the list is already sorted, there would be no swaps. So if we go through a pass without swapping anything, then definitely at that stage the list is already sorted. So I'll do something like this in this algorithm. I'll take a variable and name it flag and set it to 0 before making a pass. And once this condition ai greater than ai plus 1 is true for any I, then we will have to swap and we will set this flag as 1. And now when we will come out of this loop after a pass, if flag is 0, then there has been not even one swap. So we do not need to conduct any more passes, so we can break out of this loop, the outer loop, and this way we will avoid making redundant passes once the array is sorted. Now with this modification, if we input an already sorted array to the function bubble sort, then this particular loop will execute only once to figure out that it's already sorted. So the time taken, if we were considering this as taking some constant time c in the worst case, the time taken will be c into n-1 only. So this will be the best case for our algorithm. Our algorithm will be big O of n in the best case. In the average case, somewhere midway after making, let's say, n/2 passes, we will exit the inner loop. If we will deduce the time complexity expression, it will still come something like an square plus bn plus c kind of expression. So in average case also, this will be big O of n square, and in worst case the inner loop will also run n-1 times and we will be big O of n square. Bubble sort is in place and stable sorting algorithm, and we just deduced its time complexity, which is big O of n square in the worst case. This is it for this lesson. Thanks for watching. In our lessons on sorting algorithms so far, we have talked about 2 of the sorting algorithms, selection sort and bubble sort. Now in this lesson we are going to talk about another sorting algorithm named insertion sort. Insertion sort is not the best sorting algorithm in terms of performance, but it's a little more efficient than selection sort and bubble sort in practical scenarios. Insertion sort is also a pretty intuitive sorting technique, so let's see what it is. To explain the logic of insertion sort, I'll once again use the example of cards. So let's say we have a set of cards in our hand and we want to arrange these cards in increasing order of rank. There are a couple of intuitive ways to sort a set of cards in our hand. One of the things that we can do is, initially we can keep all the cards in our left hand and we can start taking cards one by one from the left hand, and we can start building a sorted arrangement in the right hand. Our first card is 9 and there is no other card in right hand, so 9 will simply go into the right hand. Now we will take the next card in our left hand, which is 3 in this case. Now when we will take 3 to the right hand, we will insert it before 9 to make sure that the cards are sorted. At any stage during this whole process, the left hand will be unsorted and the right hand will be sorted. Now the next card that we will pick is 6. Now when we will take 6 to the right hand, it will have to be inserted between 3 and 9. And now the last card that we will pick will be 4, and 4 will have to be inserted between 3 and 6 in the right hand. And finally we will have a sorted arrangement in the right hand. I have used 2 hands here, but if you see, this can be done in one hand also. The idea is pretty simple. What we are basically doing is we are dividing the set of cards into 2 subsets, a sorted subset or a sorted part and an unsorted subset or unsorted part. Initially all the cards are in unsorted subset and the sorted part is empty, and we are picking up one card from the unsorted part at a time and inserting it into the sorted part. Let's say we have something like this. We have a boundary here, and let's say cards to the left of this line, this vertical line, are sorted and cards to the right of this vertical line are unsorted. So initially all the cards are in unsorted part. Now we will pick up one card at a time and insert it into the sorted part. If there is just one card, we simply move it. Now we pick up the next card from the unsorted part. It's 3. It will be inserted before 9 in the sorted part. Now we'll pick 6, and 6 must be inserted between 3 and 9. And finally we will take 4, and 4 must go between 3 and 6. It should be inserted between 3 and 6, and we are done once our unsorted subset is empty. Now when we want to write a program to sort a list, we can do something similar to what we did for the cards. So let's say we want to sort a list of integers given to us in the form of an array. Let's name this array A. We have 6 elements in the array, so we have indices from 0 to 5. What we can do is we can start by saying that we will divide the array into 2 subsets. Initially elements till index 0 will be part of the sorted subset or sorted half, because if you have one element in a set, the set is always sorted, and all other elements are part of unsorted subset. And now we will go on picking elements from the unsorted subset, and we will keep on inserting them into the sorted subset. So we will kind of keep expanding the sorted subset till unsorted subset becomes empty. At any stage, let's say the cells in blue are part of the sorted subset. Now at this stage I'll pick up 2, which is the first element in the unsorted subset. Programmatically this will mean storing the value in some variable. Let's say the name of the variable is value. So all we have done is we have said something like value is equal to A1, but for the sake of understanding, let's assume that we have taken out 2 from that position and we have created a hole there at that particular position. Now what we will do is, to insert 2 into the sorted part, into the sorted subset, we will shift all numbers greater than 2 in the sorted part by 1 position to the right. We have only one element at this stage in the sorted subset, 7, which is greater than 2, so 7 will be shifted 1 position towards right, and the hole will go to position 0. And now we will fill up 2 at position 0. We will fill up 2 in the hole, and now we are sorted till index 1. Now once again we will pick up the first element from the unsorted part, so we will create a hole like this. Remember, there is no actual taking out of 4 from this position. We are just filling up 4 in another variable and assuming that there is a hole at that particular position. Now once again we will shift all the numbers greater than 4 by one position to the right. We will do so one by one. We will start at position 1 and see if the number is greater than 4. 7 is greater than 4. So 7 will be shifted to index 2 and the whole will now move to index 1. Now we will look at 2. 2 is not greater than 4. So no more shifting is needed. We will simply put 4 at index 1. And now we are sorted till index 2. And now we will pick 1 from the unsorted part. And once again we will start shifting all the elements greater than 1 in the sorted subset. One position towards right. 7 is greater than 1. So we will shift it and the whole will now move to index 2. Number 4 is also greater than 1, so it will also shift. Number 2 is also greater than 1, so whole will shift to 0, and we do not have any more numbers greater than 1 to be shifted. So we will move 1 to this whole, and now we are sorted till index 3. And we will repeat the same insertion logic for 5 and 3 as well. For 5 we will have to shift only 7, and for 3 we will have to shift 7, 5 and 4. So finally 3 will go at index 2. So finally we have a sorted list. This particular in-place logic of shifting and inserting elements to sort a list is insertion sort algorithm. And now let's quickly write pseudocode for this algorithm. I'll write a function named insertion sort that will take two arguments, an array and the number of elements in the array. Let's say the name of the array is A and the number of elements in the array is N. Now initially we are saying that we are sorted till index 0. So we will pick up elements from 1 till n minus 1, and at each step we will insert the element at its appropriate position in the sorted subset. So in our code we will run a loop starting index 1 till n minus 1, and first we will create a whole by taking out the value to insert in another variable. So temporarily we will keep ai in this particular variable, and then I'll take another variable to mark the position of the whole. At this stage whole is at index I, and now we need to shift all the elements greater than the value to be inserted one position to the right. While whole is greater than 0 and the element at index whole minus 1 is greater than value, we will shift the element at index whole minus 1 to the whole. So now our new whole will be index whole minus 1. When we will find a smaller element than value in the sorted subset, so this particular condition will be false. We will exit the while loop, or we will exit the while loop when whole will be equal to 0. So there will be no more elements to shift. And finally when we will come out of the while loop, we will put the value into the whole. And this is our pseudocode for insertion sort. I'll quickly walk you through this particular code and show a simulation with this particular example. So we are running this code with this particular array. We will start with I equal 1. So value will be 2 and whole will be index 1. And now we come to the while loop. Whole is not 0, so we can be sure that there is an element before it, and we can access the element at index whole minus 1. Whole minus 1 is 0, and the element there is 7, which is greater than the value 2. I'll mark the whole with this color orange. And now we come here, we'll say a whole, the element at index of whole should be element at index whole minus 1. So 7 will now be written at index 1, and our imaginary whole will shift to index 0. And now in the while loop this condition will be false, whole is equal to 0. So we will come here, we will fill up 2 at this particular position at index 0. And now I will be incremented, so value will be 4 and whole will be index 2. 7 is greater than 4, so we will shift it and the imaginary whole will go to position 1. And now a whole minus 1, which is 2, is not greater than value, so we will come out of the while loop and we will write 4 at this particular position, and we will go on like this. For 1 we will shift all the numbers in the sorted subset. So finally we will have a sorted array. Sometimes the whole may not shift even by one position. We will not even go inside this while loop. In that case, it will mean just taking out the value and inserting it again into the hole. It will happen when the number to be inserted will already be at its appropriate position. So this is pseudocode for insertion sort algorithm for you. Let's now try to analyze the time complexity of this algorithm. We can try calculating the running time expression for this algorithm. Simple statements in a program execute in constant time. By simple statements, we mean statements having simple operations like assignment, arithmetic or logical operations. Like these are simple statements. Let's say these statements will take some constant time c1. They'll together take some constant time c1. These two simple statements will together take some constant time c2. And this particular statement will take some constant time c3. Now for our algorithm, these two lines will always execute n-1 times. And how many times will these two lines execute inside the second loop? Well, it depends. It depends upon the input. When we will have a sorted array, then we will not go inside this while loop even once, because this particular condition will never hold true. And this particular statement with cost c3 will also execute n-1 times. So overall time taken in the best case will be equal to c1 plus c3 into n-1. There will be some additional cost to increment counters and all, or to do these comparisons inside this condition for loops. Let's assume that they are accounted for in c1 and c2 respectively. Oh, this one should be n-1 in bracket. So we have a polynomial like a(n plus b, where a and b are some constant in terms of c1 and c3. And whenever we have a polynomial like this for the running time, it belongs to the set big O of the highest order term in the polynomial. So this will be big O of n. So insertion sort is big O of n in best case. We will have a worst case when we'll have a reverse sorted array, something like 5, 4, 3, 2, 1. In that case, for I equal 1, the statements inside the while loop will be executed once. We will have one shift. For I equal 2, we will have two shifts. And we will go on like this. For I equal 3, we will have 3 shifts. And for I equal n-1, we will have n-1 shifts. So overall cost will be something like c1 plus c3 into n-1, and 1 plus 2 plus 3 plus all the way till n-1 times c2. And if we will evaluate this arithmetic progression, we will get n into n-1 by 2. And when we will reduce this whole expression further, we will get a polynomial something like a(n) square plus b(n) plus c, where a, b and c will be some constants in terms of c1, c2 and c3. And this will belong to the set big O of n square, which is another way of saying that for very high values of n, the rate of growth will be pretty similar to the growth of n square. These lower order terms will not matter. If you're not aware about time complexity analysis and big O notation, we have a complete series on time complexity analysis. You can find a link to it in the description of this video. In average case, for ith position, we will make I by 2 shifts. And if we will try to calculate the time expression, it will again be some polynomial of the form a(n) square plus b(n) plus c. So for average case also, we will be big O of n square. Even though insertion sort is also big O of n square for worst and average case, the number of comparisons and shifts in insertion sort in all practical scenarios is a lot less than selection and bubble sort. So it's considered to be better than selection and bubble sort. So this was insertion sort and its time complexity analysis. Thanks for watching.